The point of this is that I haven't made before is that I alluded to it. Some of these ingredients we're using, or most of them, they're not pure materials. They contain something that we want, but they also contain other stuff. And so that's what this chart is sort of showing. That whiting, dolomite, wood ash, soda ash, and the borates, those are boron compounds, they really only contain fluxes. That's about the only reason we use them. And also, so that's why I have them only in that column. Now, the potash feldspar, and I've actually given you the chemical formula there, even though we're using it because it contains potassium oxide, it also contains aluminum oxide, and it also contains silica. So it actually has all three things in it, maybe not in the right proportions, but all three things in it you need to make a glaze, right? Because it's got the potassium oxide, but it's got the stabilizer, and it has the glass former. And as a matter of fact, if you heat potash feldspar up high enough, you get a glaze. And that's, in fact, what Shino glaze is. The original Shino glazes were essentially feldspar, and that's it. Melted feldspar. So if you heat them high enough, and they don't get, the other thing that's interesting, if you probably know about Shinos, it's impossible to make a Shino glaze run. Because when this stuff melts, it's really, really thick liquid. It doesn't get liquidy at all because it happens to be in the right proportions with the right amount of aluminum oxide to not get runny. So it melts and forms this very thick, gloppy kind of glaze. And that's what the first Chinos were. Basically, they were melted feldspar. But so this is the point, at least, that the feldspar actually contains these other things. The same way with the nepheline cyanide, it contains potassium, which is the K, sodium, and it also contains aluminum oxide and silica. So the same way you can melt nepheline cyanide by itself. Spodumene, that's another one. It contains, if you look at the formula, it contains lithium oxide, which is why we use it, but it also contains aluminum oxide, and it also contains silica. Not in great proportions, but it does. So one of the points here is that when we're making up a glaze recipe, we have to keep in mind what might be in one of these ingredients, even though we're not intentionally doing it. So when I'm adding a feldspar to a recipe, and I'm doing it because I want potassium oxide, let's say, as a flux, I have to keep in mind, I'm already going to get some aluminum oxides and some silica, so I have to compensate with that in the other ingredients. I can't put as much clay in, maybe, to get the alumina, because I'm already getting some from the feldspar. So this is part of the reason why formulating glazes is really complicated. Because I'm not using pure ingredients. I'm not using just the oxides. I'm using these combinations of things, and I have to keep that in mind. And then if you continue down the table, talc, you notice I've got it in two columns, because talc, it's magnesium silicate, so it is giving me the MgO, the magnesium oxide I want, but it also contains silica, so I'm getting some glass former when I use talc as a raw material. So if I use, going up above, if I use dolomite as a raw material, all I'm getting is magnesium oxide. But if I use talc as a raw material, I'm getting magnesium oxide, plus I'm getting some silica. So I have to know that if I'm designing a glaze recipe. Okay, and then in clays, I've got down here, well, the only thing, they basically contain no fluxes, but they do contain the stabilizer, the aluminum oxide, which is why I have them in that column, and they do contain the glass former, obviously, because there's a lot of silica in them. Clays are aluminum silicates. So I'm getting two of the three ingredients, which is why, remember I said before you can start off making a glaze with ash and clay? Because the ash gives my fluxes, and the clay gives me my alumina and my silica. So just those two ingredients, and I've got, in theory, everything I need to make a glaze. And then lastly, silica is just that, this is one of the rare cases where we can get a raw material or ingredient that only contains exactly what we want and nothing more, and that's silica. Powdered silica is just it. There's nothing else in it. There's no other impurities. There's no gas. It's just silica. So when we get silica, we're just getting a glass former, period. And that's probably the one ingredient also that we can get that's probably purer than just about anything else. It's just silica. So we're lucky in that respect. Any questions? Excuse me, any questions on that? Okay. So how do we use this information now that we have it? And as I mentioned earlier, the ingredients that are in a glaze affect all the glaze properties, not just the final melted glass. So what I thought we'd do is we'll talk a little bit here about, I got a couple of things that talk about like the different aspects of a glaze and how these ingredients can affect it. So let's say preparing a glaze batch. Here's some things to do about. Suppose you're preparing a glaze batch and you need to substitute an ingredient for another one. Maybe, and there are a couple of reasons for this. Maybe the recipe calls for something that's no longer available. There are mines open and close all the time. There used to be a kind of feldspar, for instance, called Kingman feldspar. Well, that mine is long since gone. But when it was in operation, people were using it to make recipes. So you'll see a glaze recipe that'll call for Kingman feldspar or some other kind of feldspar or some other mineral, and they're gone. They're not any, but the recipe might be great. So there are certain things you need to follow, certain rules, if you want to make that recipe, but use a substitute. So one of the main ones is, if you're substituting for a feldspar, you need to know whether it's a sodium or a potassium feldspar. That's the biggest thing. So if that original kind of feldspar was a potash feldspar, contained potassium, then you can't substitute a sodium feldspar. You got to substitute another potassium feldspar. So this is where some of this terminology can drive you nuts, because you run across something like Kingman feldspar and you go, I don't know what it is. Well, fortunately, now you can go online and look it up. And you can say, okay, it'll tell you it's a potash feldspar. So then you can say, okay, what kind of potash feldspar do I have that I can use as a substitute? So the big issue with the feldspar is be stick with the same type. Substitute potassium feldspar for potassium and sodium for sodium. And clay, for kaolin, for example, there are lots of different sources and different kinds of things. And again, you want to stick to as close as possible as you can. And some of them are, again, are the terminology like there's a kind of ball clay called OM4, which stands for Old Mine 4, number 4. You know, they get inventive names for these things. So you might have a recipe that just says OM4, 12%. So you need to know, and you say, well, I don't have it. Whatever it is, I don't have it. So you need to look it up and find out, okay, it's a ball clay, and then you can probably say, okay, I can substitute probably any other kind of ball clay is close enough for it, but you want to use, so then you say, okay, I know it's a ball clay, I'll swap it another kind of ball clay. So we're really lucky now with the internet, actually, we can look up some of these obscure ingredients, at least find out what it is, so that you know what to substitute in its place, okay? Now, there may be, like, as I say, I mentioned before, there are some ingredients that you just may not have. Maybe they're out there. Like a recipe might call for petalite, which is one of these lithium minerals, and it's not that common. It's not that common a glaze ingredient. There was a period of about 30, 40 years ago when well-known potters were purposely designing glazes with obscure ingredients so they could look sort of very sophisticated. That's my personal opinion. Because there was no reason to use those ingredients. It was just like then their name became attached to, oh, that's the petalite glaze master. It's like, who cares? Because there was no reason to use them except that they were kind of exotic. So if you don't happen to have, and you can still get petalite, it's expensive, and there's no reason to use it. But the common substitute is spodumene. So if you see a recipe that calls for petalite and you don't have any, you can substitute spodumene, but not directly, because the amount of silica in the spodumene is different than petalite. So you have to do a little bit of a calculation, which I'm not going to go into here, but you have to do a little bit of a calculation to compensate for the extra amount of silica, because it's not a direct substitute. They both provide lithium oxide, but the silica, the rest of it, is not the same, and you have to compensate for that. So some things can be direct substitutes, other things are close enough that you can use them, but there's a little compensation you have to do on the side to make up for the fact that they're not exactly the same. Another aspect of preparing a glaze batch, suppose you want to use, and we talked about this a little bit, you want to use a different ingredient to get the same oxide. And we talked about that a little bit. So for instance, like I mentioned, like whiting and wollastonite. If I'm looking for calcium in a glaze, I could use either one of those. I could use whiting, or I could use wollastonite to give me my flux calcium. Whiting is basically only going to give me calcium oxide. Wollastonite is going to give me calcium oxide plus silica. So I have to do a little bit of a calculation there to compensate for the fact that I can't substitute those directly. Even though I'm using them both for calcium, and they're giving me calcium, they're not direct substitutes. And the dolomite and the talc is the same thing. Dolomite and talc both contain magnesium oxide, but they're not direct substitutes. The dolomite will only give me magnesium, or at least it won't give me any silica, whereas the talc will also give me silica. So I have to keep that in mind. So if I had a recipe, let's say, and it called for dolomite, and I said, well, I don't have any dolomite, but I got a big bag of talc, I'll just put some talc in. I couldn't put in the exact same by weight amount because I'm also adding silica. I'm changing something that I wasn't planning for. Okay? And there's an exception to that. Gerstli borate, I mentioned how it's still available, but eventually they're going to run out. And when Gerstli borate became less available, one of the companies, or several of the companies, developed a frit that would replace it. So there is a frit that's a direct substitute for Gerstli borate, and that's ferro 3134.
I remember that.
Ferro, what? Yeah, ferrofrit 3134 is a direct substitute for Gerstli borate. So if you don't have any Gerstli borate, you can substitute 3134. And they did that on purpose because people were using Gerstli borate, and for a while there it wasn't available. So they developed this frit that substitutes for it. So any recipe that has Gerstli borate in it, and if you don't have any, you can use 3130. And I say ferro. When you specify a frit, you should name the company because there are different numbering systems. I mean, it's unimaginative labeling, but typically industrial. So 3134 is a specific glass composition made by Ferro Corporation. So it's better, if you can, to use the company name with it, because PEMCO, there are a bunch of other companies that use them. In some cases, the numbers are the same, or almost the same, or at least they're confusing. So it's a good idea to say Ferro 3134, and usually most people don't. You'll just see a recipe that just says 3134, and you have to know that that is a frit, and it's made by Ferro. And you want to be able to look at it and say, well, what's it doing? Well, that's a flux. That's giving me a flux or something like that. And I've got another page here that shows some examples. This next page that says chemically identical glasses. And this is just, what I wanted to show you here was, I can make up the same glaze from different raw materials. So all this is showing is that glaze 1, the ingredients are feldspar, whiting, kaolin, and silica. And glaze 2, it's feldspar. And now instead of the whiting, instead of the whiting, I'm using wollastonite, remember, because they both give me calcium, and I'm using kaolin, but I don't need to add any silica. So I've got the second columns basically show that chemically they have exactly the same composition and the same formulas, but I'm making the same glaze from two different recipes. So I'm still using feldspar, but not the same amount in the second one. Instead of using whiting, I'm using wollastonite, but I'm getting some silica from the wollastonite. So I don't need to add any silica, and I'm using clay, but a slightly different amount. Suppose you have a glaze that settles out, and this is where we can start to allude a little bit to like looking at a glaze recipe and maybe seeing how it behaves in real life. Suppose you have a glaze that I mentioned earlier that like frits tend to settle out really hard. And I also mentioned that clay, and in particular bentonite, helps to keep things from settling out. So if you have let's say you have a glaze that settles out, that you like it, but it settles out into concrete in the bucket. If you look at the glaze recipe, assuming it's not a commercial glaze, then you have the recipe, you can look at it and say, well, is there much clay in the recipe? Because if there's some clay in the recipe, that should help solve it. If not, you can add some. You could add a little bit of bentonite to the recipe, up to about 2%, and help this settling problem with your glaze. So that would be a case where you'd look at the recipe and just look at it and say, okay, I've got a bunch of frit in there and a bunch of other stuff. Do I have anything that's going to help it from settling? And the answer might be not much. So there's a good case where you'd say, okay, I'll add a little bit of bentonite to it, and that will help my settling problem. And by much, if you look at a glaze recipe and it has 3% clay, that's nothing. That's not enough to do anything. If it has 10%, then you shouldn't have that problem. But a lot of recipes and especially since frits are sort of combination ingredients, a lot of times you'll have a glaze that's frit and one or two other things, and that's it. And everything, it might have frit and a feldspar and silica or something, and it's going to settle out into a rock. So there's a case where you just look at the recipe and see, keeping in mind that I need something to keep the glaze in suspension, perfect candidate to add some bentonite to it. And the other thing is, what can happen sometimes is you might have a glaze. Have everybody heard the term thixotropic? Like you get a glaze, what it means is you get a glaze that when you go to stir it, it seems to be really hard to stir. It's kind of almost like jelly. And the more you stir it, the runnier it gets. And finally it gets thin enough where you can sort of stir it. That's thixotropic. And that can happen because you've got too much clay in the recipe. Now that isn't necessarily a problem. It is sometimes, but that can be, you can say, well, what is with this glaze? I start off and it's like pudding, and I finally stir it and I can get it to the point where it's liquid enough where I can dip things in it. And an easy way to confirm that is you look at the recipe, and if it's got 20% clay in it, that's probably the reason. Application and drying. Do you get cracks? Like, does your glaze crack and when it dries?
Yes, and then it falls off.
And then it falls off. And one of the main causes for that is too much clay in the glaze. And again, I'm keeping in mind here that there are a lot of bad recipes out there. Or there are I've seen recipes that people swear by and they say, oh, I love this glaze. The only problem is it tends to fall off when it dries. It's like, so why are you working with that glaze? Fix it or get a different glaze. But there are a lot of recipes out there that have one or more things. They may have a real virtue, but they also have one or more things that makes them, really a pain in the butt to work with. And that's a common one I'll see. People say, I love this glaze, but it really cracks badly when it dries. It's like, okay, well, then you can do something about that. And one of the main causes is too much clay. As you're probably aware, clay absorbs a lot of water. So if I have a lot of clay in a glaze recipe, when the glaze dries, the water leaves it and the clay shrinks. And when the clay shrinks, the dried glaze cracks and falls off. There is a way you can fix it, and one of the ways you can do it is there's a little calculation involved. What you do is, there's an ingredient called calcined clay. This is clay that's been heated in a kiln, and you've changed the composition so that it no longer absorbs water and it no longer shrinks. So if you have a glaze that has a lot of clay in it, you take some, let's say it's EPK, Edgar Plastic Kaolin. You take some EPK, you put it in a bisque-fired bowl, and you heat it up in your kiln to about red heat. And that operation is called calcining. What you're doing is you're chemically changing the clay, and it no longer is going to absorb a lot of water, but it still kind of works. It still has the same ingredients in it. And then you substitute part of that calcined clay for the other clay in the recipe, and it reduces the amount of shrinkage. There's a little bit of calculation you have to do because you've changed the clay a little bit. And then during the application, the drying, if you have a glaze that's cracking and shrinking a lot, and you have the recipe, look at the recipe. I sort of almost guarantee that there's going to be a lot of clay in there. So then you have to decide, okay, do I want to try to fix it, or because there isn't, or if you can't, then just unless you want to live with it, can you find another glaze that will give you the same effect that doesn't have that defect to it? Firing temperature and the range, and this is the fluxes that we talked about have an incredible wide range of effects on glazes. And one of the things they affect, and I alluded to a little bit, is the melting temperature or the firing temperature. Different fluxes work better at different temperatures. So one of the differences between low fire glazes, mid-range glazes, that is cone 6, and high fire glazes, cone 10, is the fluxes that they contain. Lithium, sodium, and potassium work the best at low temperatures. And calcium and magnesium and strontium and barium, calcium and magnesium, work the best at high temperatures. When I say work the best, that's when they become active. That's when they start to react with the silica and act. These are fluxes. So that's when they start to become effective fluxes. And so when you look at glazes, sometimes you can look at a recipe and you can tell what cone it is just by looking at the ingredients, because you can say, oh, look, there's a lot of sodium in there and there's hardly any calcium, magnesium. That must be a lower temperature glaze. That's one of the things you can do. Okay? And so the fluxes have a big influence. This is just one of the effects of the fluxes, is they pretty much, they have a big control over the firing temperature of the glaze, where it's going to melt. Most low temperature glazes, really low temperature ones like earthenware glazes, they're primarily sodium. Sodium is a really good thing for reacting with silica and melting it at low temperatures. It works at high temperature. you don't need as much as high temperature. If you're going to melt at high temperature, you don't need as much of the sodium because it's so active that you don't need as much. But it's a very effective. But for instance, I can't make an earthenware glaze with magnesium oxide. It simply won't work. It's not getting to the temperature where the magnesium reacts with the silica and starts melting. So I can't use magnesium oxide as a flux at low temperature. I can only use it at mid-range and above where it's getting hot enough to start to do something. So that's one of the differences between these different kinds of glazes is what's the flux? What's the flux that's controlling the reaction? So for instance, and we alluded to this a little earlier, like the three materials, nepheline cyanide, I mentioned that contains sodium, sodium feldspar, that contains sodium, and potassium feldspar, that contains potassium. They're related, but they melt at different temperatures. Nepheline cyanide melts at the lowest temperature of those three. Nepheline cyanide, soda feldspar, and potash feldspar. So nepheline cyanide is used a lot in cone 6 glazes because it tends to melt a little lower and a little sooner. Soda feldspar melts at a little higher temperature, so you can still use that for cone 6, but it also works really well for cone 10. Potash feldspar melts a little higher, and that's used more for cone 10 than cone 6. So again, there's the three different sources of fluxes, and they tend to be associated with different firing temperatures just because of where they become active. So like among these, so like nepheline cyanide, because these are kind of similar, nepheline cyanide and soda feldspar and potash feldspar, they're all very related, but there still is a difference in the temperatures at which they're used because they melt at different temperatures. So I say nepheline cyanide, really common cone 6 ingredient. Yeah, I can use it at cone 10. I don't need as much of it because it's more active. But it's especially useful at cone 6, whereas potash feldspar is not so useful at cone 6. It just doesn't melt as readily at those temperatures. Okay? So this is something, if I was designing a glaze, I would for one or the other, I'd pick one of those two. Or I had a case a while back where somebody sent me a recipe that they said it was, and I've got others I'll show you later, that wasn't melting quite right. And it was supposed to be cone 6. And I just looked at the recipe and said, well, the only feldspar in is potash feldspar. That's why it's not melting right. So you could just a quick glance at the recipe could say, you can't have 40% potash feldspar in a cone 6 glaze and expect it to melt well. It's not going to melt at those temperatures. So that was just, whatever the source of that error was, it was just a bad recipe. And just took a quick look at the glaze. And you say, well, that's the reason why it didn't melt. It wasn't your firing, it's the recipe. A really good glaze doesn't just have one flux. Because ideally, when you're melting a glaze, I mentioned this earlier, you don't want the glaze to all of a sudden go melt like ice melts. You hit a temperature and it goes. What you want it to do is to melt over a whole temperature range. You want it to start to melt, and as the temperature increasing, it melt a little bit more, and then melt a little bit more. And so every time it's melting, a new ingredient is dissolving in the glass that's forming, and it's melting until finally you get up to the higher temperature and it's done. You don't want it to melt all at once. So in a really good glaze, you might have 3 fluxes. You typically would want 2. You might even want 3 or more. You very seldom want just 1. Because just one is going to melt at whatever temperature that flux melts at. So by having a series of them, you start to heat it up, and one flux starts to melt, and it makes a little bit of melty stuff, and then you heat it up a little more, and now a second flux kicks in, and it starts to melt and do its thing, and more things dissolve, and that's what you like. And what that does is, that gives you a long firing range. That's what gives you a long firing range, is if I have one melt, that thing that melts at one temperature, then nothing happens until I get to that temperature, and all of a sudden, boom, it melts, and then I hit it a little more, and it's overfired. So by having a mixture of fluxes that melt at different temperature, that's what allows me to extend the range so it's not so temperature sensitive. And this is the reason, I'll get to you in just a second. I'm not ignoring you completely. I'm trying to, but I'm not. No, that's okay. And so this is the reason why, this is another fact, is that low temperature glazes, earthenware, are more temperature sensitive than cone 6, and they're more temperature sensitive than cone 10. General rule. That is a rule that's pretty reliable. Most cone 10 glazes have a pretty wide firing range. Cone 6, not so much. Earthenware temperatures have a very narrow firing range. The reason why is because I'm much more limited into the fluxes I can use at low temperatures. I don't have as many fluxes I can use in a low temperature glaze. They don't work. In a high temperature glaze, I can use anything in there. So I can have 6 different fluxes in a high temperature range glaze and get this really wide firing range. Cone 6, I'm kind of in the middle. I can have a few, not as many as cone 10, but I'm not as limited as cone 06. But 06, there are only a couple of fluxes I can use, which means that there's a very narrow temperature range that the glaze matures. So I have to be much more precise in my firing of earthenware glazes and hit them right dead on to get the best effect. To cone 10, I can have a wide range because I can have all these choice of other fluxes that are available to me. Everybody follow that? Runny glazes. I mentioned if you don't have enough of the stabilizer in a glaze, it's going to be runny. Now, in some cases, this is actually intentional. Is everybody, or have you heard of these things called macrocrystalline glazes? Those are the glazes that have these big rosettes of crystals like on the surface, typically cone 6. Well, those glazes are intentionally made with very low aluminum oxide content because, and I didn't mention this earlier, the second thing that stabilizers do, in addition to preventing running, is they prevent crystal growth. So in order to make a glaze where I'm trying to encourage crystals to form, excuse me, I can't have much aluminum oxide. But then I'm paying the price, I'm getting a runny glaze, and there's no way around it. So these macrocrystalline glazes that have these beautiful rosettes that form it's intentionally made with very low aluminum oxide to encourage crystal formation. And the glazes are so runny, they have to set the pots on special little tripods with special little cups. And typically then the tripods are knocked off with a hammer after firing, and you grind the bottom of the pot to get the glaze off it. There's no way around it. Yeah. And that's why people that do that kind of pottery are usually kept in rubber rooms in between when they're working on the pottery. Now, it could drive you crazy. I mean, it's incredibly laborious because you literally have to grind the bottom of every pot. There's no way of it. The glaze just flows off in a puddle. I should have brought one with me here. I've got some examples. I have a little cup that was a test piece. Cup's only about this big, and it was glazed with one of those glazes. And it was on a little slab, and there's a huge puddle around the bottom of this little tiny cup where probably half the glaze ran off on the bottom. But so there's a case where this is done intentionally, but if you have a glaze or a glaze recipe that you find that is runny and you like it otherwise, one of the solutions is add a little bit of clay or do some tests and add small amounts in increasing amounts. Now, at some point, and there's going to be a range there that it'll tolerate a little bit of clay and it'll make it less runny, and it won't show up in the other properties. But at some point, you're going to reach a level where it'll start to show up. It'll affect some of the other properties. One of the things that aluminum oxide does is it mutes colors. So it might start to make the colors more pastel. In addition to not running, it might start to make the colors change a little bit. It also might start to make the glaze matte. So most glazes, you can add a little bit of clay if the running isn't too bad and just solve the running and not noticeably affect the glaze. If you start putting in more alumina, then you're going to start to see some other effects. Yeah, the glaze won't run, but it starts getting a little more matte and the colors start getting a little more subdued. And you can decide whether you like it or not, but that's the solution anyway. That's the easiest solution, a little bit of clay. Crawling. Everybody know what the glaze defect called crawling is? This is where the glaze on a fired piece sort of parts. And you have like this, there'll be a weird irregular shaped patch of where you can see right down to the clay body with maybe a little skin of glaze over it. Most of the glaze is around the edge. The glaze has sort of parted. And crawling is probably the most difficult glaze defect to diagnose because there are like 25 different things that can cause it. But one of the things that can cause it, so that if you have crawling on a thing, then you've got to go down this mental checklist. Well, did I do this? Could it be this? Could it be this? And by a process of elimination. But one of the things that can cause crawling is too many fine particles in the glaze. And especially like a lot of clay. And again, what that goes back to is if the glaze shrinks a lot when it dries on the pot, when it shrinks and cracks a little bit, the glaze is actually moving. It's because it's shrinking, and when it's moving, it's breaking the bond that it has with the clay underneath it, and that's weakening it. So instead of the glaze melting and sticking down, it pulls back and sticks to itself when it melts. So too many fine particles in the glaze recipe, especially clay, can encourage crawling. They don't necessarily cause it, but they encourage. And crawling is one of those weird things because it doesn't show up until you fire the pot. you know, you have this bisque-fired pot and you glaze it and you say, oh, I got a great glaze application. It's beautiful. No cracks, nothing. It looks perfect. And then you fire it and then it crawls. And so, but you caused the crawling when you applied the glaze. The root cause of crawling is a poor bond between the dried glaze and the clay underneath it. That's the root cause. So anything that can lead to that can promote crawling. The other thing that can do it is so I mentioned, so these are three things that can lead to crawling. A lot of fines or clay in the glass. We mentioned the high viscosity, where when it melts, if it doesn't get very runny, then it doesn't spread. It tends to stick to itself. And the other thing is, if you have a lot of opacifier in a glaze. An opacifier is something you add to the glaze to make it opaque, and the most common one is Zircopax. Everybody heard of that ingredient? We're going to talk about that, but you add it to make the glaze opaque. Tin oxide will do the same thing, or titanium oxide will do the same thing. They make the glaze opaque. So you just take a clear glaze, you put this in it, and now you've got an opaque white glaze. Well, if you add too much opacifier, that can make the glaze crawl. So if you get a glaze, and again, this is sort of like reverse now. You get a glaze, and and you want the shiny white glaze, and you put it on your pots, and it crawls all over the place. One of the things to do, it's easy, is look at the recipe and look at how much opacifier in it. If it's got 20% opacifier in it, that's the problem. That's way too much.